Okay, so we were looking at what is beta equivalence yesterday, right? And we said, okay, there is, so we call two terms to be beta equivalent if we can evaluate both of those terms to um, some m prime, right? So there is some m prime that you can get by applying multiple steps of beta reduction, right? And finally, if you end up with a term that is equivalent, right? So which is we capture that by saying from M1 you can take multiple steps of beta star, right, to get to M prime, and you can take multiple steps of beta star to go from M2 to M prime. Then we say that those two are beta equivalent. And we saw some examples, right? So this is an increment function returned using the variable x, and this is also a successor function returned using variable y. These two are beta equivalent because both of them evaluated 2, and they're also alpha equivalent because you can just go from one to other by renaming, right? But these two functions, OCaml functions, are beta equivalent but not alpha equivalent, right? You cannot go from here to here just by renaming the variables. So okay, so that gets the intuitive meaning of beta and alpha equivalence applied to OCaml, right? Okay, so as we have seen, right? So lambda calculus is very sparse. It's very Spartan. So it doesn't have too many operators. But it turns out that you can encode non-termination just using lambda calculus, and the example is not even very complicated. So here is the omega um, term, right? So omega expression in lambda calculus is precisely this expression, which says um, lambda x applied to x applied to the same term, lambda x applied to x. So what happens when you beta reduce it, right? So when you try to reduce it, the only thing that you can do is apply this function to the second function. So you'll take this whole thing, right? That will be substituted for x, and there are two x's here. So this will be replicated twice. So there is one here, there is one here. We reach the same expression as where we started with, right? And you can keep on doing this. We will never reach a beta normal form. So we will never reach a state where we can say there are no beta reduxes left. This is a non-terminating program. This is like a program that you can write where you loop infinitely. And this is sort of the defining feature of being Turing complete, right? You can write these programs which are non-terminating, and this is very easy to describe in lambda calculus. So such terms, right? These sort of terms, right? The term here, the term omega here, which doesn't have a beta normal form, right? Which when you start evaluating doesn't end up with the value, essentially a beta normal form. Those terms are said to diverge. So this is just what we use in programming language terminology, but all it means is if you start evaluating this term, you will never end up with the value. So an OCaml equivalent of this is have a recursive function foo, which just calls foo again, right? That term is said to diverge. Yeah, okay. So the interesting bit is, so what we have seen so far is that the reduction rules for lambda calculus were non-deterministic, right? They gave you several different options to apply. And we had seen some of the examples earlier where we said, oh, you can choose to reduce either the left-hand side of an application or the right-hand side of an application, or somewhere in the body of the expression, right? So you can choose multiple different ways to reduce lambda terms. And it turns out that based on the term that you choose to reduce, you can end up terminating the program. Whereas if you choose a different term, you might not terminate, right? So Church-Rosser theorem only says something about when all of the reductions terminate, right? So it only says, okay, you start from somewhere. If you reach a beta normal form, then those beta normal forms will be alpha equivalent, right? But it is possible that if you choose certain terms to evaluate, then you might end up with non-termination for the same term. Right? Here is an example. Right? So um, I have a constant function that takes an x and always returns y. And on the right, I have this omega operator. Right? If I apply this function to this term, what I get is this whole omega term is substituted for x, which is not used. So all you get is y. Okay, so this term reaches a beta normal form. Whereas because we have this option to also evaluate the right-hand side term of the application, if you start just focusing on the right-hand side term, then we have non-termination, right? This is the same as what we have seen earlier. So this is exactly the execution path that we have. So you apply, you substitute for x, this lambda x dot xx, you get the same thing. You can keep doing this forever. So this is one of an interesting parts of reducing lambda terms. Because you have non-determinism, it is possible that some evaluation may lead to beta normal form, but while others might not. Right. So um, that's a property that is due to the fact that we have non-determinism in the application of rules for evaluation. So this sort of leads to this interesting question, right? So imagine what is a high-level intuition here. Imagine you are describing a program, right? And you don't have multiple threads, or this program is not distributed, right? You want, if I write down a program and you look at the program and say, okay, this program evaluates to 0, right? There is no non-determinism anywhere. And I look at the same program, you give me the same program, I say it evaluates to, it doesn't terminate. It just keeps on going, right? So it is non-terminating. This is not something that we would want in a real language, right? If you sort of think about real languages tends to give you an idea of what happens in a deterministic fashion. They try to be as deterministic as possible, right? If you write a program, there is one behavior for this program or a set of behaviors, right, based on the inputs. And that's the set of behaviors that you want. You don't want it to differ. You don't want it to have non-determinism where it is not necessary, right? So a non-determinism might be a fact because your program communicates to the external world, right? So maybe you want to send an email or wait for an email. The fact that an email is sent to you is a fact of the external world that you cannot control. But if you just write a program that does none of this non-determinism, right? You want the program to be deterministic. So what we have seen for the beta reduction in lambda calculus so far is it is non-deterministic. You can choose several different ways to reduce the program. And in particular, if you have a possibility of non-termination, then the program will have non-deterministic semantics, right? So you can either get to a value or keep running forever. So for this reason, what we have is in lambda calculus, we have several different reduction strategies, right? So reduction strategies are different deterministic ways of reducing lambda calculus, right? So that's the high level idea. And this fact sort of closely informs how real languages are implemented. We'll first look at what these reduction strategies are, what a few of these reduction strategies are, and then we can take these reduction strategies and place them into boxes that match with real languages. Okay. So yeah, so as I mentioned before, the beta reduction that we've seen so far, right, is known as full beta reduction. Full beta reduction allows you to reduce any term. So any redux in the term can be reduced. So that's full beta reduction, and that is why we have non-determinism. Yeah, so here is full beta reduction, right? So you can Non-determinism arises because if you have a pattern Mn, you can either reduce M to M prime, or you can reduce N to N prime. Right? This gives you the non-determinism. Yeah. And so, okay, so let's look at, here is another example, right? So we will use this running example as an example for studying other reduction strategies as well. So I'm not saying anything new here. I'm just presenting one more example of full beta reduction, but this is useful to see. Okay, so we have this big term here, right? First, what we will try to do is, we know lambda xx is the identity function, right? It takes some x, returns the same x. So for convenience, we'll just name it as ID, right? Um, and whenever you see ID, imagine that that is lambda xx, right? So this is just for readability. So in full beta reduction, you can dive deep into some term, right, and reduce it, because you can always apply, um, you can always choose to reduce within a lambda, right? You can also choose to reduce within a lambda if something is a lambda. So given this term, you can first choose to reduce the innermost redux, right, which is ID to Z. And what does ID do? If you apply it to anything, it just returns the same thing, right? So you get Z as a result. And then this whole term becomes lambda Z, Z. Then you can choose to reduce this term, which is ID applied to ID again. So this becomes lambda Z, Z. And this is ID applied to lambda Z, Z. So you get lambda Z dot Z. Right? So this is one way of doing full beta reduction. In So this is the first strategy, reduction strategy that we are seeing, right? We saw full beta reduction. This is the second reduction strategy that we are seeing. So this is known as normal order strategy, right? So what it does is it reduces the leftmost redux first. So look at the lambda term that you want to reduce. If you can reduce the leftmost term, you reduce that, right? And then you have to reduce the outermost term, right? So it is reducing leftmost, outermost. Let's look at the example, right? Just to make it concrete, what I mean by leftmost, outermost. We will look at a formal definition of this, but it is useful to see an example first before we look at the formal definition. So here we have ID. You cannot reduce this ID, right? So that's the leftmost one. But also we have an outermost expression, which is that this ID applied to this term, this whole term, right? That's the outermost term that we can reduce. So we reduce that outermost term first. So what happens with the outermost term? We just, because that's an ID, we just get this term again, right? So this term is the same as the term here, right? Because ID just returns the same term. And again, we have an outermost term, right? The outermost term is um, just ID applied to this term. So again, ID returns the same term. So it returns this whole term. Okay. And finally, we cannot reduce this. So this is just a lambda, right? This is not an application. So at this point, you have to sort of dig in, right? So because it's a plain lambda, you sort of look at the body of the lambda and start to see whether there is a redux there that you can reduce. So this lambda z remains as it is, and then we can see idz. So that reduces to lambda zz because idz just returns z, right? So that's normal order strategy. So the idea is that you start reducing the outermost term. If there is no outermost term, you do the leftmost term. And if you are done with the leftmost term, you move on to the next leftmost term and keep on going. So, okay, so the other thing that I forgot to mention is we are using this beta hat, right? For full beta reduction, we just use beta. I'm just using a different symbol here just to say it's a different reduction strategy. Okay, so It's just a matter of convention. So just to, whenever you see a beta hat, what I'm referring to is normal order reduction strategy. Okay. So let's see how this works. So I have an implementation of different reduction strategies. So here is 3 reduction strategies. For now, we are going to focus on normal order reduction. So it takes some lambda string and then returns some string that represents a lambda expression. And you can optionally choose to disable printing each step of the reduction, right? So that's forget what this type is. I haven't explained to you this facility in OCaml. OCaml has the ability to provide optional arguments. This is not important right now. You can just pick it up as you go. But this is sort of saying the name of the optional argument is log, and the type is bool, and question mark says it's optional. Okay, so but I'll say nothing more regarding this type. You don't need to know anything more. So what I'm doing here is I am calling eval normal, which is the normal order evaluation strategy. I am evaluating this on the term here, right, which is the same term as here, right? It's just written out using our syntax. And if you want to pass an argument to these optional arguments, you can pass them by name, right? So you say, you use a tilde, right? And you say the name of the argument is log, because that is the name of the argument expected here. And the value that you want to pass is true, right? Again, I'm not going to say anything more, but all I'm saying is evaluate this term using normal order strategy and then turn on the logging, right? So let's look at what happens when I evaluate it. So the result is lambda ZZ, right? That's what we have here. That's what we have here. And we started with this term, right? Lambda XX, this whole term, lambda XX, this whole term. So it doesn't highlight what is being reduced, but you can sort of follow along, right? Because it's a normal order strategy, it's going to reduce the outermost one. So I get this term as a result of application. So we get this. Then because this is also an identity function, you get this term as a result, which is the same as this term, right? And because this is a lambda, you have to dig in and reduce. So this is an identity function applied to Z, so you get Z. And you have a step-by-step way of looking at what the normal order reduction performs, right? And finally, you end up with lambda ZZ. Okay, so that's normal order reduction strategy in practice. We can also formally define normal order reduction strategy, right? So this is a bit more involved than the earlier reduction strategy that we saw for full beta reduction, precisely because can you take an example with t terms? So you want an example with 3 terms, is it? Okay, so let me do this. So here is, when is it outermost or rightmost? So okay, so here is so okay, so let's look at this term, right? There are 3 terms here. First term highlighted by this green brackets, right? Second term and the third term. So in so of course the way to read these terms is like this, right? Which is you have a because our function applications are left associative. You have a left term like this, and then a term that is applied to. So what is leftmost says is in an application, right? If I have an application, you always reduce the function argument first before reducing the value. That's what it's saying by leftmost. And outermost captures the fact that because there is an application here, right? E1 applied to E2, you have to perform this application before, say, you can perform this application, right? There is a reduction possibility here. In full beta reduction, you can go ahead and reduce this as well. So if I execute this, right, we see that full beta reduction, sorry, normal order reduction first reduces this term, right? Lambda xx applied to lambda xx is just, this is identity function, right? So it just returns the same identity function again. So this is what we have here, right? And then it proceeds as normal. So the difference is that what leftmost is saying is reduce the function argument before the, reduce the function LHS of an application before the RHS of an application, right? And then don't reduce somewhere within the body of an expression if you have an outer application. That's all it's saying. Okay, good. So we will actually make it formal here, right? So I'm not saying this is more clear than what I had explained, but it is much more formal. It's this is what you will take to convert the strategy into an implementation. Okay, so what's going on here? So it has a few more premises because we want the reduction strategy to be deterministic, right? At any point in the reducing this term, only one of these rules is applicable. Okay, that's what we are going for. So because when we write inference rules, we don't have this order of writing these inference. We don't say first try this rule, otherwise try this rule, otherwise try this rule. All of these rules are equally applicable. We simply prevent other rules from applying. We always, when you want to write a deterministic reduction, you organize the rules such that there is only one rule that is applicable. Okay, so that's the reason why it's a little bit complicated. But beyond it, I would say it's not too complicated. Okay. So first thing that we observe here is the usual rule, right? The substitution rule. So if you have lambda xm and then apply to n, then wherever you find x, replace that with n in m. So this is the usual rule, right? And what is the second rule? So let's look at this property of leftmost thing, right? So if you have m applied to n, right? You just have an application. The whole lambda term is an application, and m is not abstraction yet. So what is m? M is m could be something else. M could be, say, an application, right? If m is not an application, what else can it be? So we checked that it is not an abstraction. So it could be an application or a variable. We also rule out the variable case by saying that if m cannot be reduced further. So when you have a plain variable, you cannot reduce it further, right? Then you go ahead and reduce n, right? So so that's the idea of saying, sorry, so I actually have to go to this before that. So let's step back for the moment. Let's say I explained this one, and let's go to this rule. So you have m applied to n, right? So let's just look at that first. It'll be easier to come that way. So m is not yet a lambda. So you haven't fully evaluated the LHS of an application. So this is similar to saying this example, right? Here, this is m. This whole thing is m. This whole thing is n. And m is not a lambda, right? M is not an abstraction. It's an application, right? In that case, what you do is you can go ahead and do one step of m. So go ahead and reduce m to m prime. This is what happened here, right? So we had an application here. When you reduce it by one step, we essentially do substitution, in which case we end up with this term. If you end up with m to m prime, then you say, okay, so now mn reduces to m prime n prime. So all it's saying is, if you can reduce m, go ahead and reduce m, right? That's capturing the leftmost evaluation. The next thing we are saying is, okay, we want to say after you have evaluated m all the way, right? After you have evaluated m all the way, um, you can reduce the n. But the tricky bit is this, right? If m actually evaluates to a lambda, then you have to apply this rule, because that becomes the outermost rule. So what is the only other possibility? The only other possibility is you reduce m, right? I can actually give you an example of how this works. Let's say instead of this, right, it's some foo. Okay, so lambda xx foo. So if you look at the reduction of this, so lambda xx foo reduces to, first you have to reduce this, right? Because that's the m and that's not a lambda. So once you do that, it becomes a foo. Can you reduce a variable? We cannot reduce a variable, right? Because we cannot reduce a variable, you have to reduce the right hand side of the application. That's the important thing that we are capturing. Actually, I could rewrite this rule as just saying m is a variable. Let me try to. Should I rewrite it now or later? Okay, I'll do it later. So all we are saying here is, if m is just a variable, right, then reduce n. So okay, so that's the second rule. And the last rule says, okay, finally it says, if you have lambda xm, then you can go from, if you can go from m to m prime, then you can go from lambda x m to lambda x m prime. So I sort of, so this, I wouldn't call this an easy explanation, right? But when you actually convert it to a program, it will be easier for you, because you can use the fact that pattern matching has a particular order in which it reduces. So just look at, I'll try it one more time. So the first one is this one, right? So the first case is this, right? So this is the case where m is actually not a lambda, it is not a variable. So you have to reduce m, right? That is what we are capturing here, right? So it is not a lambda, and you can reduce it, which rules out the variable case. If you can reduce it, then reduce it such that the left hand side is reduced. If m is a variable, which you cannot reduce further, go and reduce n. And the other two cases are very similar to the earlier case, right? So this sort of captures the ordering between reducing left and then reducing right. We have to twist our arms to express this in the formal semantics, but that's fine. Okay, so these rules are deterministic. What I'll do is I'll not give you a proof of why this is deterministic. I want you to think about why this is deterministic. If you find a counterexample, right? Saying, oh, here is an application of these rules which gives me non-deterministic choice. Come back to me and probably, yeah, that'll be an interesting discussion. So let me leave it at that. So that's normal order strategy, right? So normal order strategy still has this weird bit, right? The weird bit is this. We are actually reducing within the body of a function. So when we write functions in C or OCaml or Haskell or in fact any language, we cannot reduce within the body of the function, because the body of the function is not something that we can evaluate, because it requires the function arguments to evaluate. But in Lambda calculus, we can do it because the language is so Spartan. So this is not something real languages do. This particular rule, right, where you have a function and you are actually reducing within the body of the function. This is not any language, reasonable language does. So here is another evaluation strategy, which is deterministic, just like normal order strategy, but also does not reduce under abstraction, right? And all it does is, so it starts doing the outermost one first, right? So ID applied to this whole thing, it reduces to this term, right? Sorry, this term. And then you get this term here, and you reduce it again, you get this term, right? And you get an abstraction. So this evaluation strategy does not reduce under abstraction, and the evaluation stops there. So what you get now is lambda z idz. So this evaluation strategy is known as call by name. Okay, so that's why we use beta n here to distinguish that from the earlier reduction strategies. And in fact, so just to show you how this works in practice, here is call by name, right? And all it does is it reduces the outermost one, right? And then stops when it looks at abstraction. That's it. It says I cannot proceed anymore. And you can look at call by name formally. This is much more simpler than the normal order reduction. It only has two rules, right? If if uh, if you have a lambda xm and n, you just do the substitution. That's the standard rule, right? If you are able to evaluate m to m prime, then go ahead and evaluate that, right? So um, the the if you have an application, right, mn, and you can evaluate the function argument term, right, the function term, right, the function term, you go ahead and evaluate that. In particular, the thing to observe here is there is no evaluation thing for n, right? When does the function arguments actually get evaluated? The function arguments are not reduced unless they appear at the function position. So unless this appears somewhere in a position where it is the LHS of an application, this n is not reduced. Why is this a good thing to do at all? This is good because if you never use a particular argument, right, then we will never evaluate it. So if you imagine a program where you have a function that takes three arguments, and in one of the paths, right, based on the other arguments, you never use the seventh argument, say, then whatever computation that led to the evaluation of seventh argument can be completely ignored, right? So you don't need to consider evaluation of that. So it is a win there, right? But the downside is that because we delay the evaluation of the function arguments until they are needed, it is possible that they are reduced multiple times. So here is an example. So according to this evaluation strategy, all that happens is if there is an outer lambda, then you just go ahead and substitute it, right? So wherever x is here, we substitute this term, which is lambda xx applied to a, an ID function applied to a. So there are two x's here. So you have ID function applied to a once here, ID function applied to a another time, right? Now you can actually evaluate, right? So you can evaluate this term once and this term again. So you will end up evaluating ID applied to A twice. Imagine think of it pragmatically, right? So if I have some function, an expensive function that leads to some value, and I'm going to use this value somewhere. If you use this call by name strategy for reduction, what will happen is you might end up evaluating the same expensive function more than once, right? And this is not great, right? You don't want to compute expensive function more than once. You want to share the results between multiple evaluations, but you also don't want to eagerly evaluate unused expressions, right? So if you have a particular expression which is not end up being used, we don't need to eagerly, we shouldn't have to eagerly evaluate it. So there is an evaluation strategy called call by need, which avoids recomputation of redexes, which avoids this problem, right? Essentially avoids this problem, right? It's a variant of call by name. The only thing that it does is it sort of, instead of imagining these as trees, right? It imagines everything as a graph. So the high level way it does it is if you've reduced a particular expression once and it reduces to a value, it sort of caches the result. The details are not important, but um, that's what happens. So I've sort of led you down this whole path, right? We started with this reduction strategy. We then went to saying, okay, we need multiple reduction strategies. Oh, then there is call by need. Then there is call by name. Then there is call by need. We are way deep the rabbit hole, right? Why am I even saying all of this? You might be thinking if I were listening to my own lecture for the first time, I'd be thinking, okay, why is this all being taught for me, right? This is like way down the rabbit hole. What is the practical relevance of it? The practical relevance is this is precisely the evaluation scheme that is used by a popular functional programming language called Haskell, right? And Haskell calls this lazy evaluation. We are not studying Haskell in this course, but lazy evaluation has certain very nice properties, right? So it has, if you sort of look at the functional programming camp, half the people are programming in Haskell, half the people are programming in languages like OCaml, Scala, and every other language, Kotlin and whatnot. So you can read up a lot about lazy evaluation online if you want to get into this sort of thing. But the reason for going down this deep rabbit hole is that I hope that you understand where lazy evaluation sits in this reduction strategy scheme, right? So lazy evaluation is just another name for call by need. Okay, so it is used by Haskell. It was also used by this earlier language called Miranda, which is no longer actively developed. And lazy features are also present in OCaml. So you can optionally choose to use lazy evaluation in OCaml and even in Perl 6. So recent version of Perl has lazy evaluation. So these sort of features are important, right? And the way to understand what happens there is basically imagine that as a reduction strategy. And that's lazy evaluation for you. But lazy evaluation is still in a camp where it is not very common. Common languages like C, Java, C++, Python, OCaml, and every other language use this other reduction strategy called call by value. And this is the reduction strategy that you all know of, right? I don't even have to explain this to you. All that happens in this reduction strategy is if I have an expression E1, E2, E3, E4, you reduce E1 first, then E2 next, then E3, then E4, E5, E6, right? Everything reduces to a value, then perform the application, right? All it says is always reduce functions and then arguments before performing the application, right? So how does it work in practice? So this is known as call by value, right? This is the thing that we know of, right? I'm not even introducing a new strategy here. This is the thing that we know of. I'm just giving it a name. So we name it arrow BV to call it call by value. So what happens here? Let's take the same expression as before. So ID is a function, right? It's a lambda XX. We cannot reduce it anymore. So go ahead and reduce the right hand side of the application, right? So that's ID is easy. So that just returns this term, right? You get this term as a result. And now you cannot reduce either this term or this term. Again, recall that we are not reducing within a lambda because We're sort of looking at real evaluation strategies. We want to stop at, we don't want to evaluate within the body of a function. Okay. So the thing to do here is perform the application. So when you perform the application, this is an ID function. So it returns the same term as this one, right? And we stop here. And this is, we can no longer reduce this particular term because that's an abstraction. And this is what OCaml does, right? This is OCaml's semantics. Okay, so so here is an execution of that. So the same example. So you have an identity function. You have some function argument that can be reduced. So go ahead and reduce that. So you get this term as a result, right? Which is this term. And then perform the outer application. So that's an identity function. So you end up with the same term here. So we get the same term. And we don't reduce under abstraction. So we stop there. Okay, so this is OCaml, this is C, this is Java, this is Python, this is every other language that you know of. So here is call by value formally, right? So if you have an application, if you can reduce the LHS of an application, go ahead and reduce it. So if you can go from m to m prime, n, mn, then the whole expression goes to m prime, n prime. If you cannot reduce the LHS, but you can reduce the RHS, go ahead and reduce it, right? And then when you cannot reduce the RHS, right, you've done all the reductions possible, then you perform the application. Then you do the actual substitution, right? So this is call by name formally. This is what we intuitively know when we explained how function application works. Compared to lazy evaluation, we call it strict evaluation, right? So strict because there is a strict order in which lambda terms are evaluated. I mean, this is all the languages, including OCaml. Okay, so what have we seen? We have seen multiple reduction strategies. We've seen full beta reduction, which is non-deterministic, right? So you can reduce any term anywhere. So if you find a reduction in this term, you can reduce that term. Then we said, okay, full beta reduction is too non-deterministic. We don't want that. Then we saw normal order strategy. With normal order strategy, the idea is that there is determinism, right? There is only one rule that is applicable when you look at a lambda term, but you can reduce within the body of the lambda term, right? You can go ahead and reduce within the body. Then we said, okay, real functions do not reduce within the body of the lambda term. Let's implement something more real. So we first looked at call by need, right? What is call by need? Call by need says you always reduce just the function LHS of an application, right? You reduce at the function position. If there is a chance of application, just keep applying it. Don't reduce within the body of the abstraction, right? But it turns out that this has a problem because you will duplicate a lot of terms, and that's not useful for real languages, because if you have an expensive computation, you might do the expensive computation more than once. So we saw a variant of call by name called call by need. We didn't look at it formally, but call by need is what Haskell calls as lazy evaluation. Okay, so that is one. And finally, we saw call by value, which is what we know of, and we've just formally written that one. So this is all the reduction strategies that we've seen. Okay, so that's the summary of that particular section of the lecture. So we now introduce this concept of normalization. Just because we looked at several different reduction strategies, we can say that given a particular term, lambda term, right, and given a particular reduction strategy, we've seen 5, right? Given a particular reduction strategy, we can say that the term normalizes, right? The term normalizes under a particular strategy if reducing the term under that strategy leads to a beta normal form. Okay, so given a term, and a reduction strategy, we call that the term normalizes under this reduction strategy if evaluating this term under this reduction strategy leads to a beta normal form. Okay, so because we have non-determinism in full beta reduction, we have two more definitions. So we call something as weakly normalizing if you take a term, right, and a reduction strategy, and there is some reduction order in which the term leads to a beta normal form. So, but in others it might not, right? So we call that as weakly normalizing. So we saw an example earlier, right, where we had this constant function and this omega function, and we said if you choose to reduce the omega, you can keep on going forever. It will never reduce to a beta normal form. But if you choose to apply the constant function, then it reduces. So that particular term under full beta reduction is said to be weakly normalizing. Then there is strong normalization, which says that given a term and a reduction strategy, it always leads to a normal form in whatever reduction possibility, right? So weak and strong. The thing to take away here is that the distinction only appears if the reduction strategy allows non-determinism, right? You cannot talk about some evaluation leading to beta normal form and others not leading to beta normal form given a term and a reduction strategy if the reduction strategy does not allow multiple ways of reducing, right? So the distinction between weak and strong reduction is not there in deterministic reduction, right? So if there is only one way to reduce a particular term in a given reduction strategy, then it is either the term is normalizing or not normalizing, right? So there is no distinction between weak and strong normalization. Okay, so here is an example. So we've introduced lots of terms here: normalization, weak normalization, strong normalization, and so on. So here are examples to sort of make you understand these concepts better. So if you look at this omega term, right, and if you consider if you consider full beta reduction for the moment, right, so this term is not normalizing at all, right? This term is not normalizing because there is no execution path in which we get to a beta normal form. Whatever reduction strategies that you choose, be it full beta reduction, normal order reduction, call by name or call by value, in all of these reduction strategies, this term is not normalizing because it keeps on evaluating. You can keep on getting a beta reduxes and you never reach this beta normal form. So this term is neither weakly nor strongly normalizing under all of these strategies, right? And this is the example that we saw earlier, right? This is a constant function, lambda x dot y, applied to omega, right? What we saw earlier was that if you choose to reduce omega, keep on reducing omega, then you can do this forever. But if you choose to reduce the outermost redux, then in one step you reach a normal form, right? You sort of take this omega, substitute for x, and that returns y, and y is just a variable that is a normal form. So under full beta reduction, right, this is weakly normalizing, right? Because there is one path where you can get to a beta normal form, but there is another path where it keeps on going forever. Is there a reduction strategy that can normalize any term which is weakly normalizing under full beta reduction? Okay, so let me try to parse that. Is there a strategy that can normalize any term which is weakly normalizing under full beta reduction? Interesting question. I don't think there is really good question. Okay, so yeah. Yeah, I get the question. None of these actually give you that. Okay, so none of the things that we've seen so far give you that property. Really interesting question, because you're asking if there is a weakly normalizing possibility, can you always deterministically get to that? Okay. Okay. So the reason why you can't do this is the halting problem, right? So what does the halting problem say? So I mean, one interpretation is I will give me a strategy, give me a program that will take like one of these lambda terms, right? Or any program, and then say whether this program is terminating or not, right? And that is precisely the question that you're asking. So my answer to your question is such a strategy cannot exist because of halting problem. Because you will solve the halting problem if you had such a strategy, right? It's a deterministic strategy, and um, it can normalize any term which is weakly normalizing. So no, not no because of the halting problem. I think you studied halting problem earlier, right? Yes. Okay. Good. Okay. Really good question. Um, so yeah. So just to come back to what we are looking at here, right? I'll just finish with this slide. Um, this term actually normalizes under normal order and call by name, right? Under normal order, what you will do is you do the outermost one first, right? So you will do this application, and then also call by name. You will do the application first. If there is a chance of application at the outermost term, you will go ahead and do it. So both of them leads to y. This doesn't reduce under call by value, because call by value says first reduce the LHS and reduce the RHS if there is a possibility, right? Call by value keeps on reducing the RHS; it will never terminate. So this call by value does not lead to a normal form. So this is interesting, right? So let's actually look at the reduction of these terms. So here is so what am I trying to show here? I'm just trying to show these two distinctions, right? We don't have an evaluation strategy for full beta reduction because it is non-deterministic. I didn't want to complicate things, but we have evaluation functions for normal order, call by name, and call by value. So what I'm saying is this particular term normalizes under normal order and call by name, but no normal form under call by value. Let's actually see if that is true in practice. So under normal order, if you evaluate it, it's going to evaluate the outermost term, which leads to y. It's normalizing. Under call by name, eval CBN, it also reduces, right? So because call by name says, oh, if there is a application, just go ahead and do it. What happens under call by value? Call by value says, okay, first reduce the LHS. If you can't do it, do the RHS. It'll keep on doing the RHS, right? And here is what you'll see. See, it keeps on doing RHS because there is a possibility. And at some point, it says, okay, failure non-termination. So that's it. I'll stop there. I think I've taken more time than I should. So yeah, so that's normalization and different ways of evaluating a lambda term. Any questions quickly before I let you go? Is there a term that does not reduce? Yeah, omega, right? So just pick omega. So here is a term that does not normalize under normal order reduction. It actually does not normalize under any reduction strategy. Does it answer your question, Sarthak? Exclusively normal reduction. Yeah, you can. Good question. So you can do something like this, right? I can do y dot. I don't know whether it's exclusively normal because it also sort of full beta reduction subsumes normal, right? But here is an example uh, that that is sort of that is in beta normal form for say call by value and call by name, because both of them don't reduce them um, reduce under an abstraction, but for full beta reduction and normal order, this won't normalize because they can keep evaluating under an abstraction. So to answer your question, is there an example that does not normalize under normal order, but normalizes under, say, full beta, call by name and call by name? No, because call by full beta reduction subsumes normal order reduction. But here is an example that does not normalize under normal order, but does normalize under call by name and call by value. Does that sort of partially answer your question? Okay, good. So play around with this, right? So you can, there is a lot of text going on, but there is an actual interpreter that you can play around with, right? So play around with it. I think you will find a lot of interesting examples. We will see a little bit more in the next class. I think once we've sort of dug down this deep, we will sort of take a step back in the next class. I'll stop here. I've taken too much time. Thank you.